Good afternoon. My name is Ryan, and today I will be presenting my work titled Compressing Gradient Optimizers via Count Sketches. So, training deep learning models is extremely resource intensive, requiring large amounts of time and energy. For example, training a state-of-the-art transformer model takes several days on a computing cluster, requiring large amounts of electricity and computing resources. Oftentimes, we need to train several models in order to find the best one, searching over various hyperparameters and different network architectures. Now, a common tool to reduce the training time is to take advantage of data parallelism by increasing the batch size. However, increasing the batch size requires significant amounts of memory, since you need to accumulate all of the activations for the examples in the batch before performing backpropagation. So due to memory limitations, you may have to decide between either a more expressive model or a larger batch size. And the trade-off is that you may encounter slower training times if you choose to go with a larger, more expressive model. And usually, this is the one you decide to go with in order to learn better from your data. Now, in addition to the model parameters and activations, we often use extra memory to store the auxiliary variables for popular gradient optimizers. So the Atom optimizer tracks 2 additional variables equal in size to the original model. Now, these auxiliary variables do not seem to cost that much additional memory, but here's a concrete example to put things into perspective. Now, in this scenario, we are training a BERT large model on an NVIDIA V100 with 16 gigabytes of memory. Furthermore, we are using activation checkpointing and mixed precision training to save additional memory. So now you can see that the Atom optimizer uses 2 gigabytes more memory than stochastic gradient descent. And naturally, increasing the model size exacerbates this memory cost issue with the optimizer. So if you're training GPT-2 or the new NVIDIA Megatron, this problem becomes even more of a pressing issue. So our goal is, can we develop a new optimizer where we can actually get the benefits of Atom while having the memory cost of SGD? And so here is a highlighted result from our paper where we actually were able to do this. So we trained a large-scale language model, and so our count sketch optimizer uses 5 times fewer parameters than the original Atom optimizer. And so we were able to show that we have used 2 gigabytes less memory than the original one, and we were able to use this extra memory to increase the batch size and obtain faster training times. So now that I explained that what we were able to accomplish, how do we actually go about designing this new compressed optimizer? And so our goal will be, can we actually compress these auxiliary variables and maintain the convergence rate and accuracy of the full-size optimizer? Ideally, this will allow us to have the adaptive properties of the Atom optimizer while having the cost of the SGD optimizer. So our solution is we're going to use the count sketch data structure to compress these auxiliary variables. So here's a quick overview of what that count sketch data structure looks like. So say we are given n elements, which are the parameters in our auxiliary variable. We're going to use the count sketch to provide an approximation of those elements using a W by D matrix. Now, this matrix is significantly smaller than storing all of the n elements directly. So the count sketch only supports 2 operations. So the update operation, or insert, we have to add all the elements that we want to compress into our count sketch. And so each row of this matrix is assigned a different hash function. And so when we add the element into the sketch, its value is added to the parameter specified by each row's hash function. And so the basic intuition is that now, because the sketch is much smaller than the original size, we are mapping multiple elements to the same parameter in the count sketch, causing collisions. Now, the second operation is, after we've added all of our information into our sketch, we then need to query this data structure for our approximation. So for a given element, we then look up its corresponding parameters in the count sketch and return their minimum value. And so remember, we're assuming that all of the elements that we're inserting have non-negative values. So because of the collisions, we're overestimating the true value of the element. And so by returning the minimum estimate for each of the rows, we're actually getting the best overestimate possible from our count sketch. And by controlling the width and height of the sketch, we can have an accurate approximation of the element with high probability. So now, how do we put the count sketch together with our adaptive optimizer? So here is the exponential moving average, commonly used for the auxiliary parameters in the atom optimizer. So the count sketch essentially expects a stream of updates that we will insert into it. So with simple algebra, we convert the original formula for the exponential moving average into an equivalent additive form, which we can then use to add into our sketch. So now, for each time step during our optimization process, we will have new updates that we need to add to our auxiliary variable. We will then add those additive updates into our count sketch, and then after updating our count sketch, we will then retrieve an estimate for our auxiliary variable. Now we will use this estimate of the auxiliary variable and continue on with our optimizer, the rest of the optimizer's algorithm. So now, a key assumption for the count sketch is that we expect the elements to follow a power law distribution, where we see that only a small set of elements in the distribution have the largest values. And so under this assumption, the count sketch will provide a better approximation for the elements in the head of the distribution, allowing us to have a better approximation for the data set that the distribution that we're interested in approximating. And the basic intuition is that if there are only a small set of elements in the head with the most information, because of this power law, they're unlikely in the count sketch to actually collide with each other in the same parameter in the count sketch. So having this power law distribution reduces the chance of destroying the information that we're interested in keeping. So that's in addition to our experimental results and theoretical analysis, we actually tested this hypothesis in our optimizer. So we basically took different snapshots during training of the auxiliary variable and then sorted their magnitudes of their weights. So we actually were able to kind of confirm this hypothesis that only a small subset of the elements actually have large magnitudes in the auxiliary variable. And this kind of provides intuition why we believe that the count sketch is actually ideal for compressing the auxiliary variables of the optimizer. So in conclusion, our goal was to compress the auxiliary variables while maintaining the convergence rate and accuracy of the full-size optimizer. Ideally, we wanted to maintain the adaptive properties of the atom optimizer while having only the memory costs of stochastic gradient descent. And our solution was to use the count sketch data structure to take advantage of the natural power law distribution present in those auxiliary variables. And with that, we've reached the end of my presentation. If you'd like a more in-depth explanation, please visit my poster this evening. Thank you.